Hello friends, I welcome you in lecture number 5 on partial differential equations. In lecture 4 we have discussed the Lagrange method for the solution of quasi-linear partial differential equation. So we had seen that if our partial differential equation of first order is in this form, capital P into small p plus capital Q into small q equal to R, then its general solution is given by phi of uv equal to 0, where this u and v are solutions of the equations dx upon p equal to dy upon q equal to dz upon r, which are known as Lagrange auxiliary equations. So we have seen two examples in which we were able to find out these two solutions u and v by directly comparing two of these three fractions. So this we can consider as type 1 of solving Lagrange auxiliary equations. So we are going to discuss four different types of solving Lagrange auxiliary equations. So the first type is if it is possible to find out the solutions u and v by directly comparing two of these three fractions. So but we have to keep in mind that if we are comparing first two fractions, then here differentials are dx and dy. So if we want to compare first two fractions with differentials dx and dy, then we have to keep in mind that every other term must be in terms of x and y only. If we are interested in comparing fractions 2 and 3 which involve differentials dy and dz, then we have to take care that every other term must be in terms of y and z only. So if we have this type of situation, then we can find out u and v by directly comparing fractions. So this is the first type of solving Lagrange auxiliary equations. Today also we are going to discuss two more problems on type 1, and in upcoming lectures we will discuss remaining types up to type 4. So let us solve this equation, which is Lagrange equation. You can see it is y square into p minus xy into q equal to x into z minus 2y. So as we can see that it is Lagrange auxiliary equation, so we can write that given partial differential equation is Lagrange equation, and if we compare with standard form, then we can see capital P is nothing but coefficient of small p, which is y square. Capital Q is coefficient of small q, which is minus x into y, and capital R is right hand side, so it is x into z minus 2y. Second step is we have to write Lagrange auxiliary equations. So Lagrange auxiliary equations we can shortly write capital A dot E R dx divided by capital P, which is y square, equal to dy divided by capital Q, that is minus xy, and dz divided by capital R, which is x into z minus 2y. So we give this number 1. Now if we concentrate on first two fractions, then we can see in first two fractions differentials are dx and dy, and remaining terms are in terms of x and y. Same thing for okay, so we cannot compare first and third fractions, okay, because in first and third fractions differentials are dx and dz, so y must be absent. So you can see here there is a y here, and here also there is a y, so we cannot take fractions 1 and 3. Now if we observe fractions 2 and 3, then in fractions 2 and 3, sorry, I have to write it again, I erased by mistake. So Lagrange auxiliary equations are dx divided by y square equal to dy divided by minus xy, which is equal to dz divided by x into z minus 2y. So we can either compare first and second fractions dx and dy, because we have every other thing in terms of x and y. We cannot compare first and third fractions, because in first and third fractions differentials are dx and dz, so y must be absent, but here y square is present, here y is present, so we cannot compare fractions 1 and 3. Now what about second and third fractions? So in second and third fractions differentials are dy and dz, so x must be absent, but you can see here x can be cancelled out when we compare these two fractions, and when x gets cancelled out, other things will be in terms of y and z, so we are able to compare second and third fractions. So first we will compare first two fractions, and then we will try to compare second and third fractions. So first we take first two fractions. So taking first two fractions of 1, so we have dx divided by y square, which is equal to minus dy divided by xy. This implies, now we have 1 upon y, which we can cancel out, so y will cancel out here, and here also minus dy divided by x. So we try to write it in such a way that with dx we have terms containing x only, and with dy we have terms containing y only. So this is ordinary differential equation of first order, which is separable. So whenever we have separable ordinary differential equation, we can find out the solution by direct integration. So integrating both sides, left hand side with respect to x and right hand side with respect to y, so we get integral of x is x square by 2 equal to minus y square by 2 plus c1, but constant of integration can be adjusted as we wish. So here I write c1 by 2 because 1 by 2 is there in these two terms. So therefore if we cancel 1 by 2 and if we take minus y square on left hand side, we obtain x square plus y square equal to c1, which we can take as function u. So we have u equal to x square plus y square, which is c1. So the first solution is easily obtained by comparing two fractions. So this I can write as u equal to x square plus y square equal to c1. So this is our first solution. So by comparing first two fractions, we are able to write down the function u. Now we take second and third fractions, and as we can see here, x will cancel out. So we will write minus dy upon y equal to dz upon z minus 2y. So next step is taking second and third fractions, or taking last two fractions of 1. So as I said, it will be minus dy upon y equal to dz upon z minus 2y. So let me check it. So here x will cancel out if we take last two fractions. Left hand side is minus dy upon y equal to dz upon z minus 2y. So everything is in terms of y and z. So now here this equation is not separable, so we cannot solve it directly by taking integral, okay, because of z minus 2y we are not able to separate the terms dy with y and dz with terms containing z. So we have to think some another method for solving this equation. Okay, so as I observe this, I can rewrite as dz by dy. I take dy on this side and this z minus 2y on left hand side. So I rewrite this equation as dz by dy equal to z minus 2y divided by y, and this I can rewrite again as, if I multiply this by negative sign, I will have minus z by y and plus 2 times y divided by y, that is 2. This I rewrite again as dz by dy plus 1 by y into z equal to 2. So this equation is first order ordinary differential equation which is linear in z and y with z as dependent variable, which is linear in z and y. So how to solve this first order linear ordinary differential equation? So let us recall, we know that the standard form of first order linear differential equation in two variables x and y is dy by dx plus px into y equal to qx. This is the standard form of first order linear differential equation. And to solve this equation, first we have to find out integrating factor, which is nothing but e to the power integral of coefficient of y, which is px. And the formula for general solution is y, which is dependent variable, into integrating factor equal to integral of right hand side, that is qx, into integrating factor dx plus constant of integration. So this is using this formula we have to find out solution of this integral. So this is just the revision of first order linear ordinary differential equation, how to solve it. Okay, so we can use this to solve this equation. Now in this equation, instead of y, our dependent variable is z and independent variable is y. Here y is dependent variable, x is independent variable. So instead of p of x, we have p of y, and right hand side is function of z, here it is 2. So if we compare this with standard form, we have integrating factor for this equation is, I write here integrating factor equal to e to the power. Here integrating factor is e to the power integral of coefficient of y, where y is dependent variable. So here integral of coefficient of z, because z is dependent variable and coefficient of z is 1 upon y, so we consider 1 upon y dy, and integral of 1 by y is log y, so it is e raised to log y. And because exponential and logarithmic functions are inverses of each other, this is nothing but e to the power y. And general solution of this equation is, okay, this we can give this number, or we can denote it by equation number star. So the solution of star is, therefore the solution of equation star is, okay, if you compare with this, here y is dependent variable, in equation star z is dependent variable. So I write z into integrating factor equal to qx is right hand side. So in our equation, right hand side is 2. So it is right hand side into integrating factor. So right hand side is 2 into integrating factor. Here x is independent variable, in equation star y is the independent variable, plus c. And therefore integrating factor is y, so we put y as integrating factor. So z into y equal to 2 into y dy, plus, instead of c we have to write down c2 just for conveniency. Therefore we obtain y into z, integral of 2y is 2 into y square by 2 plus c2, so that is nothing but y square plus c2. So therefore y into z minus y square equal to c2. So therefore the second solution is v of xyz equal to y into z minus y square equal to c2. And the first solution is u equal to x square plus y square equal to c1. So finally the general solution of given equation is, therefore the general solution is phi of uv equal to 0. Therefore phi of u was x square plus y square and v is y into z minus y square equal to 0. Let me check value of u. Yes, it is x square plus y square and v is yz minus y square, and phi is an arbitrary function, we must mention what is phi. So where phi is an arbitrary function. So here first solution is obtained directly by comparing the fractions, and the resulting equation is separable, so we are able to find out first solution directly. But in second part we are able to compare the fractions, but the resulting equation is not separable, so we find that it is linear differential equation in z and y, and using this formula for linear differential equation we are able to find out its solution. So we come to the next problem. Solve z into p equal to minus x. So if we compare this with capital P into small p plus capital Q into small q equal to r, so we have here capital P is small z, capital Q is small q is absent, so it is 0, and capital R is minus x. So we start by writing Lagrange auxiliary equations are dx upon p which is z, dy upon q which is 0, and dz upon r which is minus x. Number 1. Now here we have 0 in the denominator of y. So whenever we have 0 in the denominator of any differential, we can equate that differential directly equal to 0. That we understand in this way. All these fractions are equal. So suppose equal value is say alpha. Then from this I can write dy divided by 0 equal to alpha. This implies dy equal to 0 into alpha, and 0 into alpha is 0. So I obtain dy equal to 0. So whenever we have 0 in the denominator, we can directly put numerator equal to 0 in Lagrange auxiliary equations. So we will keep in mind this thing. Whenever there is a 0 in the denominator, we can put numerator equal to 0 while solving Lagrange auxiliary equations. And the logic behind this is given by this. We can assume that suppose all fractions are equal to alpha, that means each fraction is equal to alpha. Dx upon z is alpha, dy upon 0 is alpha, dz upon minus x is alpha. So I obtain dy upon 0 equal to alpha, that is dy is 0 into alpha which is 0. So I can directly put dy equal to 0. Even I don't have to give reason like this. This is just for understanding why we can put dy equal to 0. So whenever we have 0 in the denominator, we will direct put 0 for the numerator also. So here I can write from second fraction I can write dy equal to 0, and this is separable. So integrating we obtain y equal to c1. Therefore u equal to y which is c1. c1 is arbitrary constant. Now what about first and third fractions? So first and third fractions contain differentials dx and dz. So and other things are containing x and z only. So we can find out the second solution by comparing first and third fractions. So we have to write taking first and third fractions. First and third fractions of 1. First fraction is dx upon z equal to dz upon minus x. Dx upon z equal to dz upon minus x, and this we rewrite as x into dx equal to minus z into dz. So you can see this is separable. Variables are separated. With dx we have x, and with dz we have minus z. So here also we can directly find out the solution by direct integration on both sides. Integrating x square by 2 equal to minus z square by 2 plus say c2 by 2. Okay, constant of integration is written as c2 by 2 because there is a 2 in the denominator of remaining terms. So therefore this we can rewrite as x square equal to minus z square, which is x square plus z square equal to c2. Therefore v is x square plus z square equal to c2, and u is y and v is x square plus z square. So therefore don't try to forget the general solution. Therefore general solution of given equation is phi of uv equal to 0. Therefore u is y and v is x square plus z square equal to 0, where phi is an arbitrary function. Now if we wish, you can write in this form also: u equal to phi of v, that is phi of x square plus z square. And if you wish, you can write x square plus z square equal to phi of y, where phi is an arbitrary function. So this is type 1, in which we are able to compare the fractions and we are able to find out functions u and v by directly comparing the fractions in Lagrange auxiliary equations. So in next lecture we will discuss second type of solving Lagrange auxiliary equations. I hope you like this lecture. Thank you very much.